I will share with you chapter 15 um, like material. Okay, chapter 15 is going to be a long one. We have so many problems to solve. Then is gonna maybe take more than recording again. I might have like 3 or 4 sessions. It depends. Now, in chapter 15, we are talking about materials that we can classify as fluids, okay? And we are going to know which materials can be or they are really fluids. We will study different laws here, concepts, new quantities. The first one is density. The second one is pressure. We will talk about the relation between pressure and depth. There is a very important principle that most, we have like its applications everywhere, like Archimedes principle, and we are going to talk about buoyancy. We will also talk a little bit about applications of we will study applications of Archimedes principle. We will talk a lot about then fluids in motion, and we will discuss the continuity equation, Bernoulli's principle or equation, and we are going to do more problems with applications of Bernoulli equation, and finally we will talk a little bit about viscosity and surface tension. Then all of these topics are really included in this chapter. Okay, now what I want to say here is the first thing I want to talk about, it is density. Okay, then here, I need to adjust my slides. Okay, then when we talk about, chapter 15, we will now go into one of the phases or two of the phases, I will say, that they are really characterized that they can flow. Okay, then we have studied before solids, and we know that solids, they have definite shape and size. For liquid, it has fixed volume, but it can take any shape, the shape of the container. The gas can be having different shapes and also volumes depending on like its case. It can be compressed, then its volume can be changed. Now, also, like one of the things that maybe I want to say here is that when we talk about solids, we have these very strong forces between the molecules, whereas when we talk about gases and liquids, they have relatively weak forces between them, and that is the reason why they can flow. Now, sometimes we say that the lead is heavier than wood, and I believe maybe this is it's not correct. It depends on the volume, and then I will say, that if we have like the same mass, we have different masses, we have different volumes. Now, what is really different between lead and wood is the density. Density means the compactness of like the structure. Like if we look inside a material that is a gas, for example, is going to be like you will have the particles or the molecules, they are really, they have distance between them. They are not very compact. When we move to liquids, we are going to have a little bit more. And when we move to solids, we will have more and more like occupying the same volume, which means it is more dense. And usually gases are really less dense. Also, I will say When we talk about different solids, we're gonna find that the compactness of the atoms inside it is gonna be different, and this is why we have different densities. Like if you compare lead and aluminum is like gonna have like very few in the same volume, whereas if I'm talking about the same volume of lead, we are going to have more of these atoms. Mass can be, density can be calculated as mass per unit volume. The SI unit, it is kilograms per cubic meters. Now, most of, I will say, the tables, they're going to give you in grams per cubic centimeter. And in order to correct, to have it in the correct units, you need to multiply by 1,000. Yeah, this table here, it is in kilograms per cubic meters. The density of water at 4 degrees Celsius is the highest density. It is 1,000 kilograms per cubic meters. We, I will say, when we talk about water is going to be is going to have less density at less than 4, and more density also, and less density also when it is more than 4. In general, if a substance has a lower density than water, it will float on water. And we are going to, maybe to do one of the questions and say when it's going to float or when it's going to sink. Also, there is a term that we are using usually. It's a ratio. We call it the specific gravity of a substance, and it is the ratio of its density to that of water. All right. Here we are talking about different densities and the range. Okay, if one material has a higher density than another, does this mean that the molecules of the first material must be more massive than those of the second? Of course, no, because as I said, it depends on the volume. Then it would simply, know that the one with the higher density is going to have more compact arrangement of molecules, but that doesn't mean that it is going to be like having more massive. We need to relate both mass and volume here. Now, if you try to smuggle gold bricks by filling your backpack, whose dimensions are 60 by 28 by 18, what would it mass be? Then I will say we're going to use the, I like to maybe talk about how we arrange these mass, volume, density. Then when I say mass is going to be volume times rho, we use rho for density. Like if I want to calculate the volume, it is mass divided by rho. If I want to find rho, it is mass divided by volume. Then these are really some of the equations that we are using. And in this chapter especially, I want you to pay extra attention to your units. Don't mix units, because sometimes you will be given quantities with different units. Here I have the volume is in centimeters cube. I have calculated that as 60 times 28 times 18. Then it is 30,240 cubic centimeters. I have the density of gold here in grams per cubic centimeters. Then it's okay. I can use it, and I can calculate the mass in grams. And it's, here I didn't specify that I need a certain unit. Okay, then you can keep it grams, or you can convert by dividing by 1,000 to kilograms. Or initially, you can find the volume in cubic meters and then multiply by the density in kilograms per cubic meters. Also, here I want to add that when we have an area and we want to convert from centimeters squared 2 meters squared, you're going to multiply by 10 to minus 4. And when I have volume and I want to convert cubic centimeters to cubic meters, is going to be 10 to minus 6. Another unit that we may encounter throughout this chapter is the volume. And if the volume is in liters and I want to convert into cubic meters, minus 3. Okay, then this was about the first topic. Now we don't want to mix between density and pressure. Okay, these are two different quantities. Now for the pressure, it is when the fluid exerts a pressure, is going to exert equal like in all directions. Okay, the pressure is defined as the force per unit area, which means force divided by area. The unit that we are using, it is a Newton per square meter, and we call that pascals or Pascal. Now, at any point in a fluid at rest, the pressure is the same, otherwise it will flow. Okay, whenever we have irregularities in pressure, we're gonna find that like if it is air, if it is a liquid, is gonna flow. Okay, then this is really something that we need to know. For a fluid at rest, there is no component of force parallel to any solid surface, and because of that, if there were a fluid, the fluid would flow. Okay, then it's just like as I said, this is the equilibrium that, and we like in this first part, we are talking about what is really called fluids statics. Okay, then it's really here we are talking about when the fluid is not really when the fluid is not flowing. Now, there is a direct relationship between pressure and force, and there is an inverse relationship between pressure and area. Now, the same force applied over a smaller area results in greater pressure, all right, because it is in the denominator. Okay, think of poking a balloon with your finger and then with a needle. Which one is easier? If one material has a higher density than another, does this mean that the molecules of first, like this is repeated, by the way. Okay, you are walking out on a frozen lake, and you begin to hear the ice cracking beneath your feet. What is your best strategy for getting off the ice safely? Okay. Are you going to stand absolutely still and don't move a muscle? Are you going to jump up and down to lessen your contact time with the ice? Are you trying to leap in one bound to the bank of the lake? Or you're gonna shuffle your feet without lifting them to move towards the shore? Or you're gonna lie down flat on the ice and crawl toward the shore? Okay, if I am this person, I will go with the last one, because by lying down, I will be able to decrease the pressure. And when I decrease the pressure, this is going to reduce the force per unit area. And then I will be able to, after that, maybe safely crawl toward the shore. Now, we are going here to estimate the pressure exerted on a floor by one pointed chair, only one, okay? And we have like the mass of the chair is 60 kilograms, and the area for one, of course, it is 0.02 cubic square centimeters. And we are going to find the pressure by a 1,500 kilogram elephant that is standing on 1 foot, okay? And it has an area that it is 800 square centimeters. Now, since like the chair, it has 4 legs, then each one is gonna receive, sorry, this is the force. Now the force, remember, it is the mass times g, but okay, and I will divide by 4 because I have 4 legs. Then like its portion of the weight that is gonna receive, it is 60 times 9.8 divided by 4. And then I'm gonna divide this by the area. I will get 710 to 7 in Newton per square meters. Now, in the case of the elephant, now the elephant is standing on 1 foot. Then it's all of its weight is acting. The 1500 times 9.8 over an area that it is 810 to minus 4, and this is going to give us 1.8 10 to 5 pascals, which is 210 to 5. And like I want you to compare, like this is of course, like I can say also pascals here. Okay, that the pressure in the case of the leg, the chair, the stool was really more the pressure. Atmospheric pressure is due to the weight of the atmosphere above us, and the atmospheric pressure as a unit, as a number, is going to be 1.01 10 to the 5 in Newton per square meter. Okay, this is one of the constants that we might need during problem solving. The unit, again, it is in Newton per meter square or Pascal. Now, there are different ways of representing or like units for atmospheric pressure. Like in pascals, I can say it is 101 kilopascal. In pounds per square inch, it can be 14.7 pounds per inch squared. In bars, it can be 10 to the 5 pascals, which is 1 atmosphere. 1 bar is 10 to the 5, and it is 1 atmosphere as well. Now, the standard atmospheric pressure, and when we say the standard, we say it is at sea level. Sea level doesn't mean that it is like this, the actual sea level. It is a level that everybody was agreed on to have it as the level that is 0 elevation, and the pressure there, it's a little bit just over 1 bar. Here are like a summary of the values. Okay, I will say also, I can say there is also when we study barometers, that this is 76 centimeters mercury or 760 millimeters mercury or 760 torr. These are all the units that we are using for the atmospheric pressure. We don't feel the atmospheric pressure on us, although it is present on all objects. This is the reason. The reason for that, it is the P internal equals the P external, and this is why the pressure does not crush us, because our cells maintain an internal pressure that balances. Now, there is a term that we are using, which is, we call it gauge pressure. Now, the gauge pressure, it is the total pressure minus the atmospheric pressure. Okay, then the gauge pressure usually it is calculated as rho GH if we are talking about a liquid, okay, but here we are going to talk about what is really measuring inside this tire here. And the gauge pressure is the total, this one we call it total pressure, or we call it absolute pressure. Now, when we are talking about static equilibrium in fluids, we are talking about pressure and depth, okay? And we can say here that if we have a specific area, we are talking about the force is going to be m times g. The mass is rho times the volume. And then also the volume can be written as A times H. Then finally, I can find that the pressure, it's a function of H, which is the depth. Because rho in a certain fluid, rho is constant and G is constant. Then P is directly proportional to density if we are changing the fluid and depth. But if we are talking about the same fluid, then I will say the pressure depends only on the depth. Like here also, we are talking about the pressure, the total pressure. It is the atmospheric pressure plus the gauge pressure, which is rho g h. While swimming near the bottom of a pool, you let out a small bubble of air. As the bubble rises toward the surface, what happens to its diameter? Remember, as you are moving up, the pressure is the elevation is decreasing, or the height is decreasing, and also the pressure is decreasing, and therefore we're gonna have that the bubble diameter is gonna increase because the volume is gonna increase. Now, 3 containers are filled with water to the same height and have the same surface area at the base, but the total weight of the water is different for each. Which container has the greatest total force acting on its base? Okay? Now, we know that the pressure is the same as it's a function of depth only, and of course, since they have the same area of the base, then they all have the same force. Okay, I'm gonna stop here, and then I will move to